Okay, so welcome again. Before we start, are there any issues or questions anybody has about the administrative and lab scheduling and stuff like that? Or assignment handing in, none of that jazz? Alright, well, if that's the case then, we'll just start right away. We're going to continue today by starting to talk about the Simplechat application. In the last lecture, we went into some detail into the Object Client Server framework, and I just introduced this figure, which is slide 39. We're going to, for the first little bit of the lecture, going to just talk about some of the things which are shown on this slide. We'll come back to this slide after a little bit, once we've reviewed some of the details. So just a quick overview then to remind ourselves. Abstract Client and Abstract Server, they come from the OCSF. They're the only two things on this slide that come from the OCSF, the framework. Okay? And I'm not showing the connection to client part of the framework here. The rest of the stuff is what is written for the chat client application, for the Simplechat application, including the chat client subclass of Abstract Client and the Echo Server subclass of Abstract Server. Okay, so those are the two subclasses that you have to create in order to have the client-server application. In addition to that, we've got this, on the far left, the chat.if interface and the client console subclass. These two things represent the user interface subsystem of the client side of Simplechat. Okay? So let's move on and talk about a few of these things in a sort of bit of detail, and then we'll just recap in the end by looking at that diagram again. So, first of all, we've got Echo Server on the server side. In this case, our server is a very simple server. Only one class. The subclass is the class from the framework. Subclass of Abstract Server, and it does just a couple of very simple things. First of all, it's got a main method. Every program has a main method if it's going to be called a program. Okay? A program that you can start from the operating system. And the main method is what starts, and the key job that this has to do is create a new instance of itself, the class. Main method, don't forget, is a static method or class method. We said that you're not going to use those too much, but main method is one of those cases where you have to. It's a built-in thing in Java that, main method is a static method. So it creates a new instance. Now we have an instance. We didn't have an instance until that point. And starts it running. Okay? Now, because this server is going to be operating as a thread, basically what happens is that the run method starts running with the instance of Echo Server. And this run method, which by the way is inherited from the Abstract Server, it listens for clients and handles the connections until the service is stopped. Okay? So that's that part. The next thing that we have is that we have 3 callback methods implemented. Remember, these callback methods are the methods that are either hooks or slots. Okay, the first one, HandleMessage from client, okay, is a slot method that we had to implement to do something. We'll talk about that in just another slide or so. Then we have server started and server stopped. Okay, we'll also just see what those things do. The key slot method, HandleMessage from clients, all that does is whenever it gets any message coming in from a client, no matter what that message says, it's going to call send to all clients with that message. So basically, all the clients get any message sent by any client to the server. So it just distributes all the messages coming in. That's all it does. Very simple, very straightforward. On slide 41, we have the sort of core of this server. This is the HandleMessage from client code in Java. And as we can see, it's really only got 2 statements. The first one is a system.out print line, which is echoing to the screen of the server, and then the all-important line, send to all clients. Okay? Send to all clients the message that came in. So we print out the message, and then we send it out to the clients. Okay? Very simple, very straightforward. The client is a little bit more involved. The client side of the Simplechat system has 3 classes, because it has the one class that is the core, functional core, the subclass of the abstract client, and it has a user interface component, in fact, an interface in a class. So 2 classes and an interface. So chat client, our subclass of abstract client, its key job is to override HandleMessage from server, and it knows that there is a user interface out there, and that user interface is capable of displaying something. It doesn't know what display does. It doesn't care what display does. It just has a handle on, in fact, an interface called ChatIF, and it knows that this Java interface called ChatIF is capable of doing something with anything it sends to the interface. So it's going to send a string to the interface, and it knows this interface can display that string. How it does it, it doesn't care. Chat client says, I don't care whether it's a text-based interface or a graphical user interface-based interface. All I know is that I've got an interface called ChatIF, and any user interface class that implements that is capable of handling that display method, and so I'll just say display. Okay? And that's whatever it does whenever it gets a message from the server. Pretty straightforward. Then we have the client console class. Okay? Client console class is our core user interface class. And it implements this ChatIF interface and any class which implements ChatIF interface has got to implement a display method. So client console implements a display method. And client console does the user interface basically by using the system.in, system.out type of terminal I/O. So it's not a graphical user interface. Later on, you're going to be replacing client console with some code which will do graphical user interface stuff. It will also implement ChatIF. And from Chat Client's perspective, Chat Client wouldn't care. As soon as you replace client console later on with a client GUI that also implements ChatIF, Chat Client says same thing, still implements ChatIF, so it'll still work the same way. So you can change your user interface totally. You can have a totally new user interface without changing how the core of the system interacts with it. And that's part of the division of functionality between core and UI that is a very strong principle of software engineering that we want to try and adhere to. Okay? The client console accepts user interface with a loop in its run method. Okay, so this is acting as a thread. It's got a run method. In that loop, it will accept user input. So the user of the client can type stuff, which will then get sent off to the server. Okay, all the input is sent to the chat client, the core of the system, which then calls sender server. Remember, sender server is a method that is inherited from abstract client into chat client. So we've got our user interface has got to pass off to that chat client class what we want to do with the input we get from the user, and what we want to do is we want to send it to the server, and then it will get distributed, and eventually it will bounce back to us and to all the other clients. Okay, so that in a nutshell is how the client works. Any questions before we go on? Here is a piece of key code in the chat client. HandleMessage from client UI. Oh, that's interesting. This isn't HandleMessage from server. This is HandleMessage from client UI. It's a handler method that we have written in our subclass, in our chat client class, to interact with the user interface side of the client. Okay, this is nothing to do. This is our own Simplechat functionality. It's nothing to do with the framework. Okay, this is in the framework. You'll also see HandleMessage from server over there, which we've talked about. But this is HandleMessage from client UI. Okay, don't get the two confused. It will take a message, which is a string, and it's going to send it to the server. But notice that it's in a try-catch block. So it says try send to server. Now, that could fail. Okay? Can anybody tell me situations in which that could fail? What are the possible things that could have happened?
The server drops the connection.
The server could have dropped the connection in several ways. And you know, that's the generic answer. What's the specific things that could have happened? Well, the server just shut down. The server could have shut down, right? It could have crashed. It could have shut down. Okay, those are two possibilities. It could have also. Our network connection to the server could be unplugged. The server could still be running just fine. However, if that happens, then both the client and the server their sockets will detect that problem. And also, the server could have booted us off, okay, which is similar, but not quite the same. So there's a number of things that could have happened. The net result is that our socket would no longer be we would no longer be connected to the server. So if we say send to server, ultimately what that's doing is it's using our object output stream, which is connected to the socket, and that whole complex will fire off an exception. And so if any of those things have happened, by the time we get to this point, we try to say send to server, we'll get what is called an I/O exception thrown. And what we do under those circumstances is we say client UI.display. Notice the call to display again. We're notifying our user interface component that there's a problem. We're not doing it directly. We're never in this chat client class, which is the core part of our system, doing any user interface work. We're always delegating user interface work to our user interface, whatever it might be. All we know is that we have got one of these interfaces, okay, that has the display method, and we're just passing a string to that. And we don't care how the user interface deals with that. It will deal with that. We're just saying, here's some information. And then we're quitting, okay? Now, we couldn't. This is an interesting design decision. We are making the decision in this version of the design to quit when we detect a dead connection to a server, okay? There are other design alternatives. And some people suggest other design alternatives that we could do instead of just quitting here.
Try to reconnect.
Okay, one possibility is we try to reconnect. So we could have some logic in here that tries to reconnect, and maybe if we successfully reconnect, goes ahead and sends the message and never notifies the user interface, or maybe notifies the user interface of the temporary disconnection and so on. That's one possibility. What other design alternatives are there? Yeah?
You can send again.
If we get this exception thrown, we don't want to just send again, because if we get this exception thrown, we're pretty sure that we have to try more than just blindly sending again. You know, if we send again, we're almost certain to get another I/O exception unless something's really strange. Unless there's a bug in Java, effectively. Okay, so we at the very least have to try to reconnect before sending again. Okay, but there are still some other design alternatives that we could do. Yeah.
We can prompt the user and ask him what he wants to do.
Okay, we could prompt the user. Well, there's a number of things we could do with the user. We could instead of quitting, we could send his message back. Could not send message, but don't say terminating client. We could then just sit there, and the user interface is now in control. And the user interface could have a command that says reconnect or quit. Okay. So quitting directly in our central logic of the system is probably not the ideal thing. We probably want to give the user the control over doing that. The user could choose to reconnect. The user could choose to quit. Later on, we'll take this quit out in a later version of this system. Okay? Give the user more control. Any other questions? Or any other alternatives or thoughts about this? Okay, so that was the handle message from client UI. The other thing that we have is handle message from server. This is that slot that we had to fill in. And notice there's only got one statement here. Whenever we get a message from server, we do nothing except send it to the user interface. So client UI display message to string. And notice that we're converting all of our incoming messages to strings in this version of the system. All right, let's just go back and then review slide 39, just as a quick recap. Okay, the key thing I want you to understand is the use of the interface here, because this is one of the features that we want to try and encourage Java designers to use as interfaces in places like this, so that I can swap classes when I feel like. Right now we have client console, later on I can swap to a new version. Another thing I want us to think about here is what we're going to be doing as we enhance this system. Okay? As we enhance this system, we're going to be making new versions of the subclasses of abstract client and abstract server. So we're going to be creating new versions of chat client and new versions of, well, we might not call it echo server anymore because it might be doing more than echoing. Remember I told you, do not clone code, which means copy chunks of code from one place to another. Okay? The rule about not cloning code applies when you're going to be having those two versions of the code both running and both existing at the same time. What we're going to be doing in this case is we're going to be taking chat client and upgrading it and creating a new version and then saying forget about the old version. And so you are allowed in this case to copy the code of chat client and enhance it. And we're going to create something maybe called chat client version 2 or something like that. And then effectively that new version becomes the current upgraded system, and so in the old version thrown away. So yeah, you can copy code into and duplicate it to create a new version. Echo server, we're going to be doing a lot more than echoing. We're going to be doing stuff with private messages and with a lot of control commands and things like that. So we might not call it echo server. Echo server was still as our first release. Okay? And so we can copy the code from echo server into our second release and start editing it and modifying it without violating that anti-cloning rule that I talked about earlier on. Okay? So before we leave this picture, are there any questions about it that anybody still has in their mind? Okay. In the lab, you will have had some experience working with this and fixing some bugs in it. And then we move on into the subsequent labs. You're going to be making quite substantial changes, including graphical user interface work. I'm going to wrap up our coverage of Chapter 3 by talking about the risks of this chapter that we want to be aware of. Remember, in each chapter, we want to be aware of things that could be problematic, things that could be risky if we're out there developing software in the real world, things that we want to plan for and have strategies for dealing with. Okay? So one of these things we have to watch out for is poor quality reusable components. Okay? We talked about reusability at the beginning of the chapter. One of the risks is that we're going to be given pieces of code that maybe the people who develop them think they work well, but we discover that they are poor quality. And poor quality often means it might work for some specific circumstance, but in general it doesn't work for all the circumstances that one ought to imagine it for. So it might not be as reusable or as flexible as it ought to be. That's one kind of quality problem. It might have bugs that we detect in our use that were never detected by other users because they didn't use them in the same way. Okay? So we have to assess the people developing the reusable code that we're trying to reuse and only really use reusable components if the other people have been following good software engineering practices, which means that they have been testing extensively, they've been designing for flexibility, they've been designing with generality in mind, okay? For example, creating interfaces so that, the system is not tied to one specific user interface, and separating user interface out from functionality. I mean, if you get given a piece of code that's got user interface code in it, that code is much less reusable than it would have been otherwise. And also you want to make sure that the people are willing to provide active support to any software you reuse. In this course, you're reusing all the Java libraries and you're reusing the Object Client Server Framework, OCSF. Okay, well, I'm willing to support OCSF. We've been working on it for several years. We've worked the wrinkles out. We might continue to have to maintain it if new bugs are reported, or if we have new operating system releases or new Java releases where it doesn't quite work the same way. So we'll have to pay attention to those issues, deal with those as necessary. Somebody reported the other day that there was a problem on some of the machines in the lab here where clients quit randomly after a period of time. It seemed to be a random problem. Some people were having it on some computers, not on others. We'll investigate and see if we detect that problem recurring and track it down if it really is a problem. Okay? But it could also be a problem in the operating system configuration. But one of the cardinal rules of software engineering is just don't blame the operating system, the compiler. Try and see if the problem is really your own problem. Another issue which we have to worry about with reuse is compatibility not maintained. We have tried in OCSF to avoid obscure features. Okay, we've tried to make this work with all flavors of Java as much as possible. Okay, so, and to make it work on the Unix platform and the Windows platform at least. So hopefully we've done a reasonable job of that, and we'll have to continue working on that. One of the things that you can do to, if you're out in industry and you're contemplating reusing code, is to check, are other people also using that code? Because if many people are reusing the same code, then you have some confidence that if any problems come up with that reusable code, that lots of people are going to complain, and therefore the manufacturer or the developer of that code is going to feel the heat and is going to be likely to fix. But if you're the only one who's reusing the code, then it's one voice crying in the wilderness, right? So reuse code that other people are also reusing. There's a much higher probability of success. What if you're, rather than reusing code, you're developing reusable technology? Okay? Okay, so if you're doing this, you have to treat the development of this technology as an engineering project in its own right. Okay, as if you had an end-user client. Instead, what you have is a software engineer client. Okay, your other software engineers are going to be the users of what you're developing. You're developing components. Okay, but you still have to follow the same engineering principles, so that other people will actually take up on your investment and will say, yes, this is something that I can invest in. I can invest in the work of these developers because they've done a good job. So if you're on the producing side of reusable stuff, you've got to treat it as an investment of time and effort to make sure that your quality level is high enough. And you have to combat the not invented here syndrome. Okay, you're going to have lots of people out there saying, "Gee, we didn't develop that stuff. We're going to develop our own version. We don't trust you." So if you're the one who is at risk of not being trusted, you want to build confidence in your work. You want to guarantee support. You want to tell people, yes, we will support, here's how we will support it, and you want to support it periodically and give new releases so people have confidence in your work. And, focus on quality as much as you can and respond to people's needs. Okay? Just this morning, I got an email from a professor in England who's using our book, and he had some questions about some file formats that are on the website, and I immediately responded to him, and I'll deal with those issues. Okay, so you have to respond to the needs of users if you want your stuff to be reused, and it's an investment. It does cost, but hopefully you're going to pay back because people will start using your work. If it's shareware, that's one strategy. People might give you small contributions. If it's commercial, you'll get paid a decent amount of money eventually, hopefully. Okay. Finally, we have to worry about some competition. You have to always be aware that there are other things out there. For example, there are other competing client-server frameworks out there. Okay? There is a framework from IBM, for example, that is written in Java that does some of the same stuff. Okay, now, so how do we differentiate ourselves from the IBM framework? IBM's a big company, billions of dollars, okay, so they can certainly make sure their thing is high quality and probably a lot more sophisticated. So maybe our competitive strategy is to say, okay, we're not going to be ultra sophisticated, we're going to be ultra simple. Still top quality, but very simple to use. So people can plug our thing in without having to read, 100-page user manuals and fiddle with all kinds of features. Okay, so one of our objectives was to make this a simple framework. Okay? And another issue is we have to worry about divergence. Divergence is where, imagine that we produce OCSF, the framework, and somebody takes it and says, I like that, okay? And he said it's sort of shareware, I'm not selling it, so they'll just take it, make a copy, make their own version of it, and put that out on the web too. So now we have two versions that work slightly differently. Maybe they fixed some bugs that we didn't get around to fixing, or maybe they've added some features. And then somebody else does the same, and somebody else does the same. So divergence is one of the risks, that you get multiple versions splitting off, and they're not compatible with each other. We see this all the time. We see this in programming languages, okay? You've got Java, and then you've got, companies that produce their own libraries to plug into Java. Well, if you try and use the library that comes from Sun, it's not compatible with the Java GUI library that was released by IBM some time ago for use in their Eclipse project, for example. And that's an example of divergence. Microsoft often likes to diverge things as well, and always wants to produce their own versions of things. They have probably pretty good competitive reasons for doing that, but divergence nevertheless is a problem. So we have to try in our designs to combat divergence by making our initial design as general and flexible as it can be, so that there's less temptation for people to create divergent versions. And if they do create divergent versions, rather than editing our code, they've created subclasses that are still compatible with our core system. Okay, that's what we like. A little bit of divergence can be positive because it can give different innovations a chance to see the light of day, but too much divergence with totally different libraries, totally different components, just confuses the world and reduces the attractiveness of the platform as a whole. What about risks in client-server systems? One of the biggest risks, anytime, and I mentioned this before, anytime you think about producing a distributed system, which client-server is the archetypical example, you have to worry about security. You can have hackers breaking in. If you set a running Simplechat version system running on the net, on port 5555, and you don't have a firewall, you might get somebody sending a distributed denial of service attack at 5555 on your computer, and slowing down your computer. Java is going to be running furiously with your server just going away. Please don't do it, okay? I've just mentioned how you can hack. Well, please don't start doing that to your neighbors in the lab, You could easily put a little loop that would start jamming other groups and blocking their progress, right? So, it's unethical. That's basically the key, okay? And in fact, any kind of hacking at one point in time was regarded as sort of cool. These days, it's becoming more and more and more unethical. Even so-called grey hat hacking, which is sort of testing things out, is considered these days to be unethical. So, watch out for it. And try not to set yourself up to be a victim of it by trying to pay attention to some of the security issues. So one thing you can do is you can monitor the use of your port and start blocking access if you see some abuse. You can start encrypting messages. There's no encryption in this system, but you could easily plug in encryption of the transmission. You just have to create an encryption module that happens before the send to server or send to client, and then in the handle message from on the client and server side, you have the decryption module, and then everything else works the same. Okay? Another issue we have to think about is with client-server, we said there's a big advantage, and that is that you have two sides. You can independently develop clients, independently develop servers. What that opens you up to is forward and backward compatibility issues. You might end up with somebody running an old server and you've got a new client. But more likely you'll run into somebody running a new server and you've got an old client. We see that on the web all the time, okay, with old web browsers, you know, versions 2, version 3 still running, okay, and the servers are more sophisticated now, and HTTP, HTML have moved on, but these old clients still try and connect. And so what you need to do is to design your server protocols so they can still understand the old protocols that old clients might still try and communicate with. Okay? It's considered extremely bad software engineering practice to design a website that says you must upgrade to Internet Explorer version 6 to use this. Okay? You see that all the time. Okay? It's just bad software engineering to do that. It's equally bad software engineering, well, maybe not equally bad. It's reasonably bad software engineering to say, sorry, our system will not work on version 6. You know, you have to have version 4. And in fact, you know, a couple of websites I visit, one says you've got to have version 6, and one says you can't have version 6. So that, you know, you run into problems like that. So this kind of the need for adaptive maintenance and dealing with forward and backward compatibility, you've got to deal with it, keeping your end users in mind. Some end users are going to be using old clients. Okay? That's something to consider. That's in the web context, but the same thing applies for all kinds of client-server architectures and systems. And that brings us to the end of Chapter 3. Are there any wrap-up questions? Okay, let's move on then into Chapter 4. That says Chapter 4, doesn't it? Chapter 4. It's Microsoft Windows is popping up a strange little message talking about improving the performance. I really don't care about that. I think that's bad software engineering. I just want to go to Chapter 4. There we are. Okay, so you've seen an example of something not to do. Do not pop up extraneous messages asking, do you want assistance with something? Unless you really analyze with the user that you think this is really going to be useful, because that was not useful under that circumstance. It was totally ignoring my menu request to go to Chapter 4 and asking if I wanted help on doing something or whatever. I don't care what it was asking about. Okay, so Chapter 4, developing requirements. We have so far seen in this book technology issues. We've talked about the technology of reusable components, the technology of client-server architecture, the technology of networks. Before you start developing systems, you have to have an understanding of technology. Okay? Some people go out there and do software engineering. The first thing they do is go develop requirements. They go talk to the users and so on. And yes, you do need to talk to users early, and you need to develop requirements early. But I'm convinced that if you don't have a good grounding in the technology, you're going to be developing requirements which are unrealistic, which you will not be able to implement, or which are too big and too complex and so on. So that's why we started off thinking about technology and getting some grounding in that. Now we start what is the first step of any software engineering project, whether it be an enhancement project or a greenfield new development project, or even a framework development project, a reusable component project. We've got to work out what the real needs are. Remember, we said that software engineering is solving customers' problems by the development of quality software. So we've got to find out what those customers' problems are in detail. I said that requirements is the first step. It's also an ongoing thing. We do it at the beginning, but we continue to do it, even when we've moved on into design and other kinds of things. So the first thing that we want to do as part of this requirements process is what we call domain analysis. Domain analysis means that you're going to build up an understanding of how the user works, how the user's business works, how the user does his or her job, the user's technology, the user's background knowledge, and maybe not just the end user, maybe the user's clients, the user's management, the other software the user works with, so that you can talk to the user intelligently, so that you can make active suggestions, and rather than just blindly do what the user wants, you can really speak the user's language. Okay? So we talk about domains. A domain is a field of business or technology in which our users are going to use the software, in which our software will be situated. It could be computer games. It could be productivity applications for personal digital assistants. It could be emergency response for paramedics or fire departments. Okay? Could be air traffic control. Could be microwave ovens. Could be cellular telephony. Could be building bridges for civil engineers. Who knows? Could be banking. In particular, probably particular parts of banking, because banking is a very big industry. Okay? So we have to learn the lingo. One of the things that software engineers have to do, far more than other engineers, is to learn about all kinds of areas of human endeavor. Okay? So other engineers have to learn about basic science and physics and chemistry, because they're going to be using physics and chemistry. And they have to learn about other branches of engineering, because they're going to be working with other engineers. Software engineers have to do that too. That's why in the software engineering program, like the computer engineering program at the University of Ottawa, you have to take basic science. But you also have to take some business, because a lot of software engineers will be doing things where they have to work with businesses, even if they're engineering or science businesses. And a lot of software engineers will be running their own businesses too, because a lot of software engineering is done in relatively small-scale organizations. But software engineers might also work in the arts, in the humanities, in the social sciences. Okay? And so it really pays for you to say, okay, I want to build up some expertise at the university level in some area that interests me. It doesn't have to be engineering, it doesn't have to be science. It could be anywhere where there is a body of knowledge to be learned and where there's potential for software to be developed. Okay? And then as you progress through your career, you will perhaps build up several bodies of knowledge in other areas, other domains. Maybe it's music, for example. There's a lot of work in computer music these days. So if you're a musician, you can apply that. You should learn to become an expert in that area, learn about the software in that area, learn about how musicians work, etc., etc., etc. You can become a software engineer specializing in music. It would be very unlikely to be a civil engineer specializing in music, by the way. So that's one of the key things, that software engineers do work in diverse domains. In those domains, you're going to be working with domain experts. Domain experts are people who are not software engineers, but have the knowledge that you need to understand. You're not going to become domain experts. Domain experts typically have degrees in that area and have practiced in that area for years. Certainly they're knowledgeable about that area. Even if they're not, they don't have degrees, even if they're not knowledgeable, beyond a few months, they might still know a lot more than you do. We still call them domain experts. They have decent knowledge in the domain that you can learn from, and you want to try and make contact with some of these people if we're developing systems in their area. Doing domain analysis allows us to speed development, because we don't blunder into wrong decisions. We understand what we're doing, resulting in a better system that better meets the needs of the user. And also, and this is key, remember we talked about flexibility? Flexibility is central. Well, if we do domain analysis, that allows us to better make our systems flexible, because we can anticipate future extensions that we're not actually going to build in the first release. Slide 3 shows the kind of things that I think you should do if you're building a decent-sized system, and therefore you need to invest in a decent amount of domain analysis. Create a rough document. It doesn't have to be sophisticated. I'm not a fan of unnecessary bureaucracy, but I do think that it's worthwhile gathering together. Maybe it's a web document that your software engineering team can use. Maybe it's a web document that all it has is pointers to other places, but nevertheless, it has types of information that I've categorized here. Okay, so, and this is the kind of information, this document is the kind of thing that new people that you hire into your project would first read. You've done the domain analysis, you've found lots of information and tidbits that would be useful. This is a guidance to new people coming in, and it's also a reference so that if you forget something, you can quickly look it up. So this puts together all the stuff that you found in doing your domain analysis. An introduction. Where are the best places to get background information quickly about this subject? What are the key things that you need to learn, new hires need to learn if they're working in this area? Glossary. What's the terminology? Is there a dictionary out there that we can use? Are there some words that our users are using in strange ways that aren't in the dictionary that we ought to document so that we make sure that we get our naming correct, when we create classes and things? What is general knowledge about the domain that all the domain experts know? Some domain experts, when they talk to you as software engineers, will assume you know nothing and will start explaining everything over and over again. Other domain experts will assume that you know an awful lot, and they start talking above your head. And so having some of the general knowledge sort of encapsulated, you can prevent this talking over the head, because software engineers will first go here, read the information this points to, and be able to then converse with the domain experts. Who are the customers and users? What do they do? What are their roles? What are their attitudes? How many of them are there? Okay, these are all pieces of information that we really need to know up front very early on. We'll talk much more about customers and users, particularly users, later on when we get into Chapter 7. What are their characteristics? But you can find some of this out early on. What is their environment? What kind of hardware do they run? What operating systems do they run? Do they keep their software systems updated? Are they still using ancient compilers and web browsers and things, or are they more up to date? Are they running very slow systems? What's the capacity of their network? And what's the capacity of their network likely to be in the next little while? What other software have they purchased that might complement our software? Maybe we don't need to produce everything because they've already got some stuff that we can plug into. Or maybe they have some software which would potentially conflict with our software. What programming languages is their software running in? If they have contracted a lot of people to do custom development and they've got a bunch of software written in C++ and COBOL, well, maybe we should know that because we might have to interface to that. Or maybe we make our own decision that we're going to go C++ so that they maintain a consistent platform. Okay, so we need to know all these things about the environment of our customers and users as it is now and as it's likely to be in the next few years as our system gets developed. How do they go about doing things on a daily basis? How do our end users go about doing their work? Let's imagine that we're talking about hotel management and reservations, okay? So we've already listed the types of people. We've got various kinds of managers, various kinds of people who run the front desk and take reservations and book people in. We've got people in the kitchen staff. We've got we've got concierges. We've got people who run the back office. We never see them if we're hotel guests, but maybe they're in the main central office that run the finance and things like that. We've got people who go and clean the rooms. Do they use computers? Well, we better find that out. Maybe they have to log in every day to say, I'm here, and find out what rooms they're supposed to clean that day. These are the kinds of things that we need to know. And we need to know in detail what they do. So what about the people who do the front desk work? How do they go about doing their work? What kind of questions do they have to answer from guests arriving or calling on the phone? What kind of problems do guests have that they have to solve? Okay, if we're supposed to provide a computer system that these front desk staff will use, we better know what the guests' problems are and how the front desk staff deal with guests' problems. Maybe some guest gets checked into a room and then comes back down and says, I don't like this room, it has a view of a smokestack outside, I want a view of the river instead, so we have to change the reservation. How do we do that? Is there an easy way to do that? So we basically have to understand the way they do things now with their existing software, or with their manual paper-based systems, or by just talking to people. Maybe we're automating a process which right now is very informal. We need to study competing software. Competing software is essential for you to understand. Okay? Now, we have to watch out. We can't duplicate some aspects of competing software because there may be patents. Okay? A patent is a piece of intellectual property that where a company is given the right to be the sole producer and distributor and seller of this inventor unless you purchase and somebody else purchases a license. Okay? But nevertheless, even if there is a patent, we still need to understand how it works. Maybe we're going to license that patent. Okay? We might say, okay, we'll pay some money to license the patent on this technology. For example, there is a patent out on voicemail. So if you want to produce a better voicemail system, you've got to pay royalties to produce that better voicemail system. That even if it has extra features, you've still got to pay the patent on basic voicemail. But you also want to learn the competing software's advantages. What does it do nicely? And what does it do badly as well? You know, how do people have trouble with this software? Maybe it's got too many features. Maybe it's got some features that we think we could do better at. So I encourage all of you as potential people who will be doing software engineering, whenever you get the chance, sit down and use software. Even if you're never going to be using it in your careers, sit down and use it. Get experience using as much software as you possibly can. And especially when you start projects, try and get access to the competing software. Maybe you rather than buying it, you go and find people who already have it installed and try it out and say, can I just use your computer for half an hour just so I can see how the existing software runs? You know, network a bit to get some experience with competing software. And finally, what are the other domains that we need to pay attention to? So if we're developing, say, a new frequent flyer plan for an airline, we probably ought to pay attention to other kinds of point systems. So how do the systems at various kinds of department stores work? Because they're basically point systems too, right? Are there any frameworks out there that would encapsulate some of these kinds of things? Okay? Learning a bit about competing domains may give us ideas that we can transport from those domains and make our own work better. Questions? Okay, so that's the core of the kind of things that you need to do to develop a domain analysis document. Slide 4 lists 4 different kinds of, or categories of starting point that you might have for your project. There are shades of gray, but I've categorized them into 4 main areas. On the horizontal axis, we have whether you as a software engineer have to start developing requirements from scratch. That's kind of the best alternative. Or the clients have produced requirements already for you. That is where you have to be a little bit careful. Okay? Sometimes the clients, with very little knowledge of software engineering, go out and write requirements and say, I want exactly this implemented. Now, if they're not software engineers, or they're not skilled software engineers, okay, and there may be a difference, then you might end up being presented with bad requirements, and you're told to produce them. Worse, your management might have signed a contract to produce these bad requirements, and you're now the person, the poor sod who's told to develop this software that meets these requirements. That is an institutional problem in some areas of software engineering that we have to watch out for. The rule of thumb is, don't commit yourself to developing requirements produced by others until you have had a chance to do a review of the quality of the process with which those requirements were developed. Did they do domain analysis? Did they do all the other stuff that we're going to talk about in this chapter? Did they talk extensively with the clients and users? And is this really going to solve the customer's problem, etc., etc., etc.? You'll find that a significantly high percentage of client-produced requirements are lacking, and you have to make sure that any contract you sign says that you're going to be doing this review and that you won't actually sign off on developing requirements until you, in fact, believe that they do meet the customer's problem. And you can couch this in language that says, in order for us to ensure that we're solving the customer's problem, we have to do our review to make sure that these requirements are well developed. Okay? It's a professionalism issue. You have to do that. Unfortunately, sometimes you're put in a sticky situation where you can't. And so sometimes you have to, for ethical, professional reasons, you have to tell your boss, these requirements were done badly. And And we should not go and develop these as the way they are. And then you have to make a killing. But it can sometimes be a very political and difficult issue to deal with. On the horizontal axis, we have the new development, the green field, or we have the evolution of the existing system. Remember we said that the evolution of the existing system is more common. And so blocks C and D on this diagram tend to be the ones that we're going to do. Ideally, we probably want to be in A or C. Okay? But there's different characteristics of projects depending on whether they're in A, B, C, or D. Most of what we're going to be talking about now is how to go about doing A and C. We have to determine the requirements. If you're given the requirements already, what you have to do is to verify that this stuff was done. So the first thing we want to do is to define the problem. Remember we said that we're solving customers' problems. We have to make sure that we've pinned down what that problem really is. And that is not always easiest. The problem can be either phrased as a difficulty. So in a hotel management system, the difficulty might be that this hotel chain finds that they're getting a lot of complaints from guests with bookings that are incorrect, with slowness at making bookings, especially on the web perhaps. And they realize that their system is just a lousily designed system. Maybe it's using ancient technology. They want to replace this system. Maybe that's the problem, because they're having problems with the existing system. Or maybe it's a system where the technology is currently primarily manual. Maybe you have forms that you have to fill out. Okay, so maybe you come to the University of Ottawa and you've come from another university and you want to get advanced standing for courses you've already taken, and you have to fill out pieces of paper to provide all that information. And the university finds that this is a slow, laborious process for the professor who's got to do the evaluation, for the secretaries who've got to deal with entering this information in, and for the student. And so we want to produce this, do this online, so it's streamlined, can be stored in a database, fewer errors, etc. Okay? So the difficulty there is getting rid of a slow, laborious, error-prone process. On the other hand, the problem can be expressed on the positive side as an opportunity. So I look out there in the market and I see, there's an opportunity for a new game product that has some feature that's really cool and neat to take advantage of new fast networks and new technology. And so I express my problem as an opportunity in that circumstance. Okay? Now, as we said, we're going to be solving customers' problems, so we might sometimes decide that we're going to buy software. And we always have to keep that in mind. Okay? Having said that, we're going to focus on those cases where you will be developing software. So we're just going to although buying may be an option, we're going to focus on the development decision. We want to make our problem statement short and succinct. A problem statement ideally is a paragraph, preferably just a sentence even, if we can boil it down to that. Because once we have a succinct problem, we can keep referring back to it and always say to ourselves, are we actually focusing on this problem, or have we diverged? Are we doing something else completely different? So if our problem is the bureaucracy involved in getting advanced standing for courses you've taken, if that's our problem, and as we do development, we start adding features, and these features get more and more sophisticated, and we decide that we're going to hook up electronically with other universities, and then we're going to build a little mini sort of registration system, and we're going to build a fancy, ultra fancy graphical user interface that has all kinds of animation in it and stuff like that. That seems to be not solving the problem. That seems to be just creating gimmicks. Okay? And so if our problem is getting rid of bureaucracy, we don't want to create another problem, which is gimmicks and slow response time and stuff like that. We're going to use a little example of a university registration system. I mentioned our problem should be short and succinct. It should also be of a reasonably narrow scope. Okay, so down here we can see that if I was told that I was going to develop a university registration system, that there's a bunch of things that I can do in such a system. Browse courses, allocate rooms, have register students, schedule exams, do fee payment, and I put these all in one big blob. You know, we might initially say, here's all the stuff that we can do. The problem is better, more efficient registration. That's a positively expressed problem. This might be the things that come to mind first. But I might decide that that's a bit too broad. I want to have a more focused problem definition, at least for the first release. And one of the strategies to coming up with a more focused problem statement and a narrowed scope is to try and think of the higher level needs of our end users. So if I express my end users as students of a university system, and their problem is registering in courses, that's one way of expressing it. I might, however, decide that it would be better to think at the higher level. What's your real problem? Why are you really here? You know? You're really here in order to get a degree that will benefit you in your careers and at the same time to interest you. And so we might try and re-express, in the book you'll see a re-expressed version of that problem that is couched in terms of helping students to take interesting courses that will lead to a challenging career. Okay, that's a lot different from registering in courses. Boring, you know. But it has a lot of impact on the kind of system we're going to develop. Registering in courses, well, okay, we're just going to do some bare, mundane system that sort of lists, here's all the courses available in this department. Click on one to register. Now, it doesn't help the user too much, because they've got to figure out their own prerequisites, they've got to figure out which courses that they take this year will help them take courses next year, and so on. Whereas if we take the high level, you know, taking interesting courses leading to a challenging career, and finishing as soon as possible kind of high-level objectives, then that brings to mind, well, we want to help students by helping them pick courses that will lead them to the third and fourth year courses that they want to take to get their you know, to fill their interests and take the courses they're most interested in. Okay, so it gives us a better expression of what the users really need. So determine the high-level goals if they're too narrow, exclude some things if it's too broad. Down at the bottom, on the bottom right of page 6, we see that we're going to focus on browsing courses and registering. Okay, browsing courses in an intelligent way that will allow people to understand the prerequisites and the courses that this course will open up as in future, what their prerequisites are, and so on. That's what we're going to do in the first release. Maybe in the second release we'll worry about room allocation and exam scheduling. Notice that they're both sort of allocation and scheduling are similar problems. So trying to work out where to fit people effectively. So we'll leave that till later. It's a separate system even. Okay? And fee payment, well, we'll just use the existing system for now. We don't want to try and chop off too many pieces of the block at once because we get a system that's too complex. Okay, any questions about that? So the key is, make sure that you have a narrow enough problem so that you can do the work without getting too much complexity, and that you're focusing on the user's high-level goals. These could conceivably sometimes be in conflict with each other, because you could imagine that the high-level goals open up a lot more possibilities. So sometimes you have to iterate a bit. Narrow down the goals a bit, say, okay, we're not going to be quite so forward-thinking because we just end up being too complex, and we'll compromise a little bit sometimes. But nevertheless, focusing on high-level goals is something that you should at least do as an exercise. Okay, so to this point, we've got domain analysis figured out. We understand the domain. If we're doing a university registration system, we have examined other university registration systems. We know how the university bureaucracy works, how Carleton University bureaucracy works, and other university bureaucracies work, so that we can hopefully sell our system to different universities and make it generic. We know how the different types of people, the secretaries, the receptionists, the university registrar office, etc., how they all work, etc. We've defined and how the students work. Shouldn't forget the students. And how the professors work, you know, when they interact with registration. Okay? They're all important. And then we've moved on to the problem statement. We've got a problem statement that's focused, isn't too broad, and tries to tackle the high-level goals. Now, time to actually write down requirements. What should this system actually do? On slide 7, I have a definition of a requirement. You're going to be producing a set of these. A requirement is a statement, first of all, about the proposed system that all stakeholders agree must be made true in order for the customer's problem to be adequately solved. Keywords in here. It's a statement. That could be written in text. It could sometimes be part of a diagram. It's about the proposed system. That's obvious enough. All stakeholders agree. Okay, so it's not a requirement until not only have the end users agreed, and the customers agreed, and the management agreed, but the software engineers have agreed. The software engineers have got to agree that it's technologically feasible and doable within the time constraints, etc. Okay, remember, we're going to be solving customers' problems within time, cost, and other constraints. And so we have to make sure, from an engineering perspective, that really this is doable within the time and with the technology that we have. And so everybody's got to agree. Or, you know, sometimes there's some compromising required. You know, sometimes the customer's got to say, well, okay, we'll have to accept that you can't do quite as much. And the software engineers might have to sometimes accept a bit of a challenge, although be careful that you don't accept too much of a challenge that's unrealistic. Okay. A single requirement should be short and concise, easy to read, easy to digest, easy to look at and say, I know what that's saying. It's about the system. It's not about the end user or something like that. You know, there are things that belong in the domain analysis document. That's background stuff. Those aren't requirements. Sometimes people mix them together. Okay? Keep the requirements as things that are about the system and how it will interact with users. And as we said, it solves the customer's problem and stakeholders have agreed. Overall, the collection we're going to call a requirements document. There are different kinds of requirements document and different parts of the requirements document that we'll talk about in the next few slides. Okay, before I move off slide 7, are there any questions about that? Some software engineering students have told me that they find this stuff about requirements to be dry. And stuff about project management, which is at the end of the book, to be dry. And yeah, in some sense, they are. Playing with cool technology is much more exciting. Drawing diagrams of designs and thinking about design alternatives can be more exciting. But you're not going to be able to create a good, cool system unless you've done the requirements. So it's one of those core fundamental parts of any engineering process. A civil engineer has to do requirements for their bridge. A mechanical engineer has to do requirements for their mechanical systems, their automobiles. Every engineer has to do requirements. It's just part of the profession. Two types of requirements, functional, non-functional. Some people are moving away from this term non-functional and just calling them design constraints or constraints. Okay? But the standard terminology that's been around for many years is functional versus non-functional. Functional requirements are the key requirements describing what the system will do. Non-functional requirements are requirements that we think we must adhere to, but which limit our options and choices of how we can go about developing the system. They're constraints, such as what type of platform it's going to be developed on, what the cost limit is, things like that. We'll talk about these two categories now. I like to categorize functional requirements into the categories you see on this page. The inputs, first of all. Okay? What kind of data will our system be accepting from its users, from other systems, sensing in the world, that kind of thing. We have to describe these concisely and precisely and understand the kind of data that we're going to be getting, kind of data that we're going to allow. We want to be flexible so that our system doesn't crash when it gets bad inputs. Okay, we have to define these carefully and make intelligent choices about the inputs we're going to allow. Outputs. These are outputs that are presented on the screen, that are printed out, that are sent to other systems, or control messages sent to machines that our system is controlling. So robot arms, etc., etc. These are all the outputs of the system. Again, we have to precisely describe those so that we're providing good information to our end users and we're providing accurate data to other systems and in a flexible way so that other systems can use our data in a variety of different ways, perhaps. Then what data should our systems store that other systems might use? That sometimes is considered part of the outputs. I like to distinguish it. Outputs is information that's immediately transmitted over a communication channel. Storing is we create a database as part of our system that other systems might then later on tap into that database. Or maybe it's files instead. So we develop file formats, database structures as part of our development. Okay? What computations should we perform? Given our inputs, given our outputs, given the data storage, what are, from an abstract perspective, the computations? We're not talking about algorithms here. Okay, so I don't say how I'm going to sort the data, whether I'm going to use an insertion sort or a quick sort. That's design. What I say in the requirements is that this data needs to be sorted alphabetically by name, and more specifically, by family name. Okay? And secondarily by given name and if they're equal, by address or by city, for example. Okay? So that's the requirements. How it's going to be done, what algorithm will be used is design. We'll leave that till later. And then the timing and synchronizing of all the above. When do these things happen? Some systems this isn't too much of a concern. It's just whenever the user uses the system, so we don't have to specify it. Other systems, like practically all real-time systems, or all real-time systems, timing is key. We have to specify that when the user speeds up above 40 kilometers an hour, that our automatic transmission will transition into third gear. Okay? And that's the timing involved in that. Okay? Or our automatic brake system will respond within 20 milliseconds following detection of a skid. Okay? Things like that. That's timing. Our digital watch will update its display to display the next second precisely whenever it gets within 1 millisecond of whenever it gets the signal from the quartz piece of hardware. You know? Stuff like that. Timing and synchronization. Synchronization has to do with multiple threading and multiprocessing. All of these functional requirements are from the end users and customers' perspective. Okay? We're leaving out things that are not from the end users and customers. But sometimes our end users and customers are other software engineers. So if we're developing reusable software, we're developing a framework, we're developing a library, then the inputs and outputs might be the inputs, the things that our procedures are going to, the arguments to our procedures and the return value of our procedures. The data storage might be temporary internal storage that's stored by our library that other people might use. Computations might be specified more precisely. And it might be communication between two subsystems. And timing and synchronization may be things that are internal. Okay? So most of the time we'll be talking in the context of requirements for end users, but sometimes you have to think those end users are other software engineers if you're developing reusable components. As we'll see later on, we have a hierarchy of requirements. From the top-level definition for the end users to lower-level requirements of subsystems, and then perhaps down into requirements that the users never see, that are strictly for our internal use. Still requirements, because there's still going to be a level beyond this, which is design. But then there becomes a fuzzy boundary between what's requirements and what's design at some point. But that's okay, that's just part of the business. But I don't want to confuse you in this course, so in this course we'll focus on end-user requirements. Non-functional requirements are requirements where we're specifying constraints on the system, one of the fundamental things that we must do is we must write these requirements so that they are verifiable. And as we go through, we'll make sure that we can explain how to make these verifiable. Okay, so first of all, there are some requirements that have to do with various kinds of quality. Okay, qualities of reusability, efficiency, reliability, etc. So one of the categories of non-functional requirements is response time. Okay? We have to say how fast should our web server respond to the end user. And we might even couch it in terms of the client end. If a web user clicks on a link in our site, how fast should the response be? You know, as fast as possible is the answer, but as fast as possible is not verifiable. We need to be specific. We need to set objectives for non-functional requirements. So we need to say, we need to have a hard and fast rule that says, something like this, on this website, the response time for users connected on a modem, a modem running at 50 kbps, okay, shall be for all web pages in our system never longer than 10 seconds, ever, and for all web pages except those ones listed below, no longer than 2 seconds. And the ones listed below might have specific requirements because they might be doing something very complicated or specific or bringing up big images or something like that. That sets constraints on design. If we have that constraint, we know we've got to have a server that responds rapidly to our requests. Let's say it's an airline reservation system. Okay? Our server's got to respond rapidly to requests, to do the bookings, to do the lookups. We've got to make sure that we don't send big images down, that we have to optimize our images. Okay? A lot of websites don't optimize their images, but it's often possible to optimize images so they can be quickly displayed. And all those response time guidelines constrain the designers to work towards meeting those objectives. If you don't have those objectives in the requirements, you're going to get a lousy system that doesn't meet requirements. And in web systems, there's tons and tons of them. Big systems. Okay? And I'm going to use brand names. Air Canada's system, I've used it for a year on and off. It does not meet any kind of response time requirements. The new web system for the Chapters, a bookstore chain, is really bad in response time requirements. They're either overloading their server or something like that. Even the University of Ottawa system has some problems. If you want a system which really, really meets response time requirements well, go to Google. Google, the largest web search engine on the net, has to search through, vast volumes of data, comes back to you within less than a second on practically any query you do. If they can do that with the amount of data they have, anybody can do it. Okay? So, response time, you need to set good, end-user friendly response time non-functional requirements for your system. The technology is there. You just have to make sure that you require it, and your end users are going to have to, your software developers are going to have to go out and meet those requirements because it's doable. On the other hand, if you said that we're going to be displaying high-quality images of art on our website, and high quality means high resolution and so on, and art has got all kinds of sophisticated colors and detail, you cannot give 2-second response time as a reasonable non-functional requirement. You might have to say that displaying a nice picture on a modem is going to be taking 30 seconds, and if people are connecting with a modem, that's what they're going to have to expect. But on the other hand, on a high-speed connection, you could still deliver that image within 2 seconds. So you might have different requirements for high-speed connections versus modem connections. And some of you may say, but why do we still even have requirements for modems? Well, the answer is that there's still a considerable percentage of people, even in Canada and the US, that, in fact, especially in the US, Canada is ahead in high speed. There's a lot of people who use modems, a lot of people in rural areas who don't have access to high-speed connections, and if we're developing web-based systems, there's people around the world who are still years away from having high-speed connections. So we have to work still with the expectation that our users are going to be using slower computers, 3 or 4 years old, and slow connections, at least for the next few years. Throughput is a related non-functional requirement which talks about the types of systems that are processing large amounts of data sequentially, churning through inputs. You know, how many telephone calls can a telephone system route per second? Okay, that's the kind of thing. How many bank transactions can our system process per second or per minute? Okay, so systems where there's going to be transactions coming in at a rapid rate, throughput must be specified. You have to say, this bank system must be able to handle 200 bank transactions per second from our network. Maybe right now we would expect that it'll be about 2025, but we have to allow for growth, and we're going to design this system so it can handle 200 per second. That allows for bursts of action on payday and things like that. Okay? Resource usage. How much memory and how much disk space and how much network bandwidth are we going to allow for this system? This system must only use a certain number of megabytes of RAM because we don't want to force users to upgrade unless it's really critical. It must only use a certain amount of network bandwidth so that other systems can work at the same time over the same network, and only a certain amount of disk space as well. We want to bound those things, put some constraints on our designers so our designers don't just waste space. But then again, if space is available and cheap, we don't want to put unnecessary constraints on. So we have to come up with reasonable constraints for our designers. Reliability. Does this system have to be a hyper-reliable system that will never go down? In which case we're going to have to use design techniques that involve mathematical proof of the functionality. Or is this a system that has reasonable reliability, but if it goes down once in a while on non-important functions? Okay? There's ways of measuring reliability, which are the topic of more advanced courses. There's a few mentions of that in the book. You know, the number of failures per hour of CPU time is one measure. Another measure is that the number of total amount of downtime. So if the system is up 99.99% of the time, and that's our objective, that's called 4 nines, uptime. Okay, and that's a measure of reliability. 5 nines would be 99.999% of the time. So again, we want to quantify these things. Availability, I was talking about availability there in terms of 99.999% of the time. Availability and reliability are related to each other, but sometimes a system is not available, not because it crashed, but because it's down for maintenance. Okay, so reliability has to do with crashing and not performing functions correctly and corrupting of data. Availability is just purely whether the system is up or not. Recovery from failure. What capability should this system have? Should this system be able to always come up if it goes down? Or should there be user intervention required? How safe is that? What are the backup requirements for this system? And so on. Allowances for maintainability and enhancement are lists of things that are not functional requirements because we're not going to build them in the system. But they're things which we want to say, this system should be able to be expanded in the future. The university registration system, for example, should be expandable in the future to be able to deal with fee paying. We're not going to do it now, but constraint on design, keep in mind that fee paying will be added later, and don't make your design so difficult that it could never be easily added. And finally, allowances for reusability. It's not a requirement for the end user, but what parts of this system ought we to design so that they can be sold to others for similar uses? So if we're designing a university registration system for the University of Ottawa, well, maybe what parts of this system should we design generically so they can be sold to other universities in Ontario? Okay? So we'll leave it there today, and I'll try and read chapter 4. We'll hopefully try and finish it off next day.